Today we'll talk about semi-supervised learning. Semi-supervised learning. Okay, so I guess before talking about semi-supervised learning, I should really talk a little bit about both supervised and unsupervised learning. Right? Supervised learning is when we have things of the following type. Let's say we have a bunch of data points, right? Labeled say +1. Right, and then a few other points may be labeled -1. And now we get a new data point, right? Let's say the new data point is here. And we ask what is the label of this data point. Right? Supervised learning is problems of this type, where we have some labeled data, and with that labeled data, we want to build a classifier in order to be able to classify unlabeled points. Right, so you can think, for example, that maybe these are X-rays of people that have some disease or not. A +1 is if they have the disease, a -1 is if they don't. And given labeled X-rays that you get to see, and you get to see if they are labeled as having the disease or not, then you have to make some kind of very simple or as simple as possible decider, right, to be able to now make predictions on new unlabeled data points. So a very simple classifier in this case, right, a very natural classifier would be you look at +1s here, -1s there, and you could say simply anything above this line probably is a plus, everything below this line is a minus. Right? This would be a very reasonable classifier, right? It's sort of Occam's razor type thing. You want the simplest possible thing that explains the data. And then a lot of what's done in machine learning and in supervised learning type things is trying to understand how well do classifiers generalize to data you haven't seen, right? This is the generalization, right? There's usually what's so-called the training error, which is how many you get wrong by the classifier on the training data set, which here is nothing. And then there's a generalization error, which is how many we're going to get wrong when you generalize to new things. And of course, if there is a very simple classifier that explains all the training set, then it's much more likely that it will extend to other things, right? I mean, you capture what it means for a classifier to be simple or not, right? One good notion is VC dimension, for example, right? There's tools of regularization, like in statistics and so on, that are just, in a way, trying to make estimators or classifiers a bit simpler, right? There's a whole industry of these things. So in particular, this would classify this as a -1. Right? The predictor in sort of supervised learning sense would be the most obvious one would be to say that this is -1. Now, what is unsupervised learning? Unsupervised learning is what we did in the class so far, right? It's when we have a graph and we want to visualize it, we want to cluster. We get a data set and we want to learn the geometry of the data. We don't have yet any labels. We just have, say, a social network. We don't have labels of, say, which people have which preferences or which people are of a certain, say, have a certain job or whatever characteristic. We just have data, people and connections, and we just want to, say, cluster the people, find communities. We want to cluster, say, proteins in protein-protein interaction networks, right? Things of this type, right? We're trying to learn the geometry of the data, either cluster, do, say, diffusion maps and like this, without having labels, right? And that's what unsupervised learning is. Semi-supervised learning will be when you use unlabeled data to learn the geometry and labels to then be able to classify better, knowing something about the geometry. Okay, so let's say that here, right, the continuation, instead of all these 6 points, or I guess let's not think of this one, this 5, say they're X-rays, right? And they're X-rays, and the doctor goes, looks at the X-ray and sees if the patient has some disease or not. Right, and this takes time, right? It's expensive. I mean, someone needs to actually go and spend time looking at it. But maybe you go on some database, and you've taken tons and tons of other X-rays for other reasons, and you go on those X-rays, and now you you draw them, all of them, even though you don't have what their labels are, you just draw which X-rays you have. And now you have a bunch of others. Okay, let's take away our prediction. And let's say as you draw them, right? Then you see something like this, right? As you draw all the X, of course this is a super extreme case, but let's say that we draw, now we look at all the X-rays that are n-labeled, and we see that looks like this. Now that it looks like this, we see these -1s here. We see the -1s there, right? It's very clear, or at least the most naive now guess would be that this group, right, is -1s, and this one here is +1. Right? And somehow, now we would actually label this point as a +1. Right? So what happened here was the n-labeled data points, right? Points that didn't need to be labeled are telling us about the geometry of the data of X-rays. And that's helping us making better classifiers. Now the simple classifier isn't just a line, but the simple classifier is just the best way of clustering this data. And so semi-supervised learning is trying to achieve exactly this, where the in-labeled data points allow you to learn the geometry, and then the labels allow you to, from the geometry, make a good classifier. And so this is what we're going to talk about today. We're going to see how we can derive a method to learn this properly, not in cases where it's as obvious as this. Right now, of course, before we do that, maybe one thing that I should point out is one natural thing to do, of course, with the stuff that we learned, is you could just grab the data, build a graph, right? From this data, build a graph. Right? Where now with, let's say you have n data points, let's say you have x1 through xn, right? We do the same thing as we've done before, right? We build a graph where the weights are given by some kind of kernel. Right? Say, for example, right, the Gaussian kernel at some kind of scale epsilon, right? The same thing that we did for diffusion maps. Right? Where maybe epsilon would be, say, this scale. Right? So that things get connected if there's this distance, but you don't see connections here, right? So if you were to build a graph this way, essentially the connections from one of these clusters to the other would be super, super weak. And the ones here would be very strong. So this graph would just basically look like almost two disconnected components. Right? So now we have, or you can imagine that your data originally is just the graph, right? So either you do this or you start with the graph. But now you have a graph with vertices, again, edges and weights, either obtained from a data set of point clouds or from the graph itself, right? You can try to do semi-supervised learning on just a network, of course. Now, one thing we could do, of course, is we could take the graph G, do diffusion maps, like one strategy would be do diffusion maps on G. Now, because we saw in spectral clustering and the lecture on diffusion maps, you expect that this sort of opens up the geometry, right? So you expect that maybe opens these up and puts this one on the side or something of this type. And so then you could just use classical classifiers there. So a possible approach would be do diffusion maps and then do a normal classifier there. What we're going to do is going to be a little different. It's going to be a bit more mathematically principled. And we're going to find a way of, from these labeled points, finding labels for all the unlabeled data in a way that's sort of very smooth with the geometry of the graph, or also, of course, the manifold, but now we've reduced the problem to graphs. So what we'll do is we'll represent, okay, let's start by representing the labels by a vector f, right? So we'll think of our function f going now. So we start with the graph, right? We can reduce any data point cloud to a graph that way. So we start with the graph that has vertices, edges, and weights, right? This has been our object now for a while. And now we're interested in, of course, a function f that goes from vertices, right? These are the labels, say plus or minus 1. Right? We have a few plus or minus 1s already, and we want to learn the labels of the new ones. Right? So what we're going to do is we want to, of course, that, right? So okay, so let's represent this. So f, of course, is a vector in our n, because there's n nodes, and we're going to represent F1 all the way to FL are going to be the labeled nodes, right? These are going to be the labels of the labeled nodes, labels of, right, labeled nodes, right? And FL plus 1, Fn, right? These will be the labels of unlabeled nodes. Right, so these, we just take the first L nodes to be the labeled ones and the other ones to be unlabeled. Right, so we separate basically our nodes in 1 all the way through L, and then L plus 1 all the way through N. And then we say that there are U unlabeled nodes. Okay. And you know, sometimes I'm going to use notation of this, and I'm going to take L to be the set of labeled nodes, and U to be the set of unlabeled nodes, rather than just a number. But this will be clear from context, and so it will be okay. And if I were to do like capital letters, it could look like the Laplacian or something. This way is better. Okay, so now what I want, of course, I want a function, right? What is the goal? What is the goal? The goal is, of course, a function f. Right? That takes values, right? Of course, I'm just writing the same thing. It goes from the vertices to plus or minus 1. That f in the labeled nodes equals to the known labels. Right? Maybe one way to write this is that, right, f of I is equal to the label that we know fi for I from 1 to L. Right, and we want f to be as smooth as possible. Okay, this will be a bit just intuitive for now. As smooth as possible. And so we'd like f to be as smooth as possible. Okay? And the point is that the as smooth as possible, we'll have to use it in the geometry of the graph. Right? So the most natural thing, of course, is to try to minimize how much points nearby, right? Nodes that are very connected with very large weight, how different they can be. Right? So a very natural thing to do, of course, is to just take this, to minimize the sum of the squares of the difference between the values in connected nodes, weighted by the weight of the edge, right? So a very natural thing would be to minimize overall, you know, f a vector, let's say, you can just say this in Rn, where f of I, or maybe let's make it as a function. I mean, this is all the same, right? It's just a matter of notation. From plus or minus 1, such that f of I is equal to the label fi, right? This is the data. The labels of the data, right? The known labels. For I from 1 to L. And what we're going to minimize is the sum, right? Overall I smaller than j of something weighted by the weight of the edge, and just f of I minus f of j squared, right? So here we're getting something that, right? This is asking that if the weight is large, then the value should really be the same or as close to as possible to each other. But if the weight is small, it doesn't matter as much. Now, of course, the right answer to this, to minimize this totally, is to just have everything the same, but we know that some of them need to be plus 1, the labeled ones plus 1 needs to be plus 1, the labeled ones minus 1 need to be minus 1, so it's the tension, right, is that everything wants to be close to the labels, that wants to have the same value as the labels if it sees, but there's both labels of plus 1s or minus 1, so right, this will be why this is non-trivial. Right, now, of course, right, we've seen this so many times already. This is just a quadratic form given by the Laplacian. So really what we're doing is we're minimizing, right, where f is a function from vertices to plus or minus 1, where f of I needs to be equal to the data for I labeled. And we're just minimizing f transpose Laplacian of the graph f, right? Because this is just a quadratic form of the Laplacian. Now, moreover, we can actually relax the condition. So we'll relax the condition of plus or minus 1s, right? The idea being that we're going to allow for nodes to be sort of fractional nodes. They can be a number between -1 and 1, and we can even read it off as what's the certainty that we, like, if it's positive, in the end we probably are going to label it 1. If it's negative, we're probably going to label it -1. But this way we get some information also about the certainty that, if you see a 0.9, you're more sure than if you see, say, a 0.5. Right? And so now what we'll do is we'll derive the solution to this program, right? So we are minimizing some quadratic form subject to some constraints, and what we're going to do now is we're going to derive what the solution of this is. In order to find the labels, the optimal labels in this sense for the graph, we're going to derive now the solution to this, where we now relax this condition. So what we're going to be doing is we're going to minimize over f, now a function from v to just r, right, a vector in Rn, where fi needs to be equal to the data that we have for the labeled data. Right, and we're going to be minimizing f transpose LGF. Right, so in order to do this, we're going to have a bit. We're going to just write a bit of notation, which will help us. Right, we're going to separate the labeled and the unlabeled nodes in our notation, and this will help derive things a lot better. Right, so we'll take f, our vector f, of course, is a vector in Rn. Right, we're going to write it as f labeled and f unlabeled. Right, this is what we know. This is what we want to find out. And we know the Laplacian is written in terms of, right, the Laplacian of G is just D minus W. So we're going to decompose D and W as well. Right, so D is a diagonal matrix, and we'll have the diagonal, the part corresponding to the label, the degrees of the labeled nodes, and 2 L's, the unlabeled nodes, and W. And now, of course, in this language, the Laplacian is just given by, right? It's just D minus W, so it's DL minus WLL, and minus WLU minus WUL, DU minus WU. Right, and of course, because this is symmetric, of course, WUL is equal to WLU transpose. Right, so now that we have written things in this way, now we can rewrite this expression, right? Then what is F transpose LG F? Right, this is just FLFU on, right, there's a quadratic form of FLFU transpose here times this times FLFU here. Right, so what do we get? We just have to expand all this out. We have FL transpose and then DL minus WLL FL. Now we have the cross term, right? The two cross terms are the same because this is this transpose. Let's just pick one of them. Right, we pick FU. Right, minus twice that, right? It's minus this, and then the other one would be FL transpose WLU FU, but this is of course, right? This is of course just the same thing. Just the same thing. It's just a transpose, but it's a number, so the transpose is exactly the same, right? Plus now the term in FU. FU transpose du. Right, that's one. Okay, so now we have to solve for this. Right, so let's do that. I'll keep this here for us to see. Right, FL is known, right? The only variable really is FU, right? The labels of the unlabeled nodes. So really all we're doing is we're minimizing, right, over FU, right, which is now a vector in R. Okay, by a bit of abuse of notation, I'll say RU. Right, I'm using U for the set and for the number, the size of the set. Right, so we have to minimize over this, and we have to minimize this expression. Right, exactly this. But, right, so I will not write it all again. It's exactly this expression, but now in this expression we already see a few things. First of all, this does not depend on FU. Right, this term just depends on FL. So in particular, what this means is that we don't need to minimize this term. We can focus on just the other two. Right, so this is completely equivalent to just minimizing the other terms. So let's write just those. Now, okay, so we have to find a FU that minimizes this. Now I claim that du minus w uu is positive semi-definite. In fact, I'll claim that most of the time this will actually be invertible. Right, why? Because think about what this is, right? This is almost like the Laplacian of the subgraph of the unlabeled nodes. It's not quite the Laplacian of the subgraph of the unlabeled nodes, because here you get the full degree of the unlabeled nodes is not just the sum of the connections to other unlabeled nodes, but also to labeled nodes. So this is only bigger, right? This is, if you had the degree just counting nodes, just counting edges to unlabeled nodes, you get the Laplacian, which you know is positive semi-definite. You even get something more, because the nodes in general will be connected to other things. In fact, as long as there are, right, it's also hard to see that as long as unlabeled, there's no unlabeled nodes are not disconnected to labeled nodes, then actually du minus wu is positive definite, right? It's also invertible. Right, why? Let's say that, okay, let's think just for a second. Let's assume that the unlabeled nodes are a connected component. If they are a connected component, then the only possible thing in the null space of this could be the whole one's vector, because that's the vector in the null space of the Laplacian of the unlabeled nodes, right? So what I mean by this, let's take du, right, as the degrees, right, the degree matrix from U, counting only the connections to other unlabeled nodes, plus the degree matrix of unlabeled nodes counting the connections to labeled nodes. Right, now if you look at this matrix, right, du minus wu is equal to what? Is equal to du going to L plus the Laplacian of the subgraph of unlabeled nodes. Right, that this Laplacian, we know if the graph is connected, it's positive semi-definite and only has one thing in the kernel, which is the whole one's vector. So now if you think about it, as long as this matrix is not zero, then the whole one's vector, right, will give 0 here, but it will not be 0 here, right? It will pick up something unless this matrix is 0, because it only has positive things. And there's no possible cancellations, right? Because if you think in terms of the quadratic form, everything is both this and this are positive semi-definite, so there's no possible cancellations. Now, if you have disconnected components, you just have to run this argument on each one of the disconnected components. But it's not hard to see that as long as there is no disconnected component of unlabeled nodes that doesn't have any labeled node in its neighborhood, then this thing is positive semi-definite, is even invertible. Right? If we have a block of unlabeled nodes that has absolutely no connection to labels, then there's nothing we can do, right? There's no information in the labels about them. Okay? So this means, okay, it's positive semi-definite. So all this to say that if I now take FU, this is a quadratic form on FU. If I take FU, shooting off to infinity, this will go, right? Because it's positive semi-definite, this will just get bigger and bigger, right? So the minimum should be at the place where the first order optimality conditions are satisfied, right? So we just have to compute first order optimality conditions. Right, and the first order optimality conditions, in this case, right, is just taking the derivative, say that the minimum should be attained, they should satisfy that, right, twice du minus w u fu minus twice this w l fl equals to 0. Right, so in other words, right, the 2's, we can take the 2's out, of course. Right, and so what we have is that, right, this needs to be the same as this. But remember, we have that, this matrix, this du minus wu is actually invertible. In the case where you expect to be able to do semi-supervised learning, this matrix is invertible. Right, so this matrix here is invertible. And so this means in particular that we have that the optimum FU star is given very nicely by just du minus wu inverse w ul fl. Right? So the solution that minimizes this is the most smooth in this sense is given simply by this expression. Where FU star is equal to du minus W, this matrix inverse times WL FL. Now, now let's try to understand a bit about what this is doing, and then I'll show you some experiments. This is very related, for those of you that have learned things like in differential equations and so on, this is very related to the so-called harmonic extension. This essentially corresponds to the so-called harmonic extension. Right, so let me just try to make this a bit more clear. Right, we're essentially doing a graph version of the so-called harmonic extension. Right, and why? Because, okay, let's look at this expression. Right, what we have, another way of writing this expression is that du, right, du fu is equal to, right, w u fu plus w ul fl. But now let's look at entry I of this equality. Right, what do we have? Entry y, that is an unlabeled node, right? I being an unlabeled node. Right, so what do we have? What do we have in this case? Okay, so that, I think this is better. So, okay, so we take this expression, right? I just rewrote this. And now, in this way, now let's look at entry I of this to see what's happening in entry I here. Right, so what do we have? Right, this is a diagonal matrix. So all this is doing is taking the entry I, right, the degree, it's taking f at I, an unlabeled node, it's multiplying by its degree. And what is this equal to? Well, this is simply equal to, right, the sum, okay, let's write this out, of j being unlabeled, right, of Wij f of j plus the sum for j labeled of Wij fi. But you know, it's the same sum, so really all this is just the sum for all I of Wij, or for all j, sorry, in the vertices Wij fj. Okay, so let's see what we have here. Right, so what we have here is if, you know, if I is unlabeled, then we have that fi is equal to 1 over the degree, right, coming from here, the sum of Wij fj. Okay, so what we see here is that the unlabeled nodes, what they're equal to actually is exactly the average of the values of their neighbors. Okay, so we're seeing this is a property of the harmonic extensions in differential equations and so on. It's exactly, you know, it's a known property there. Oftentimes there you say things like in the solution, if you integrate around the circle, if you average around some circle, you get exactly the value at the center of the circle. Right? But here, what we're seeing is that the value of the unlabeled nodes is exactly the weighted average, where the weights are given by the weights of the graph, the weighted average of all its neighbors. Right, which is a very reasonable thing to try to do if we're doing estimation of functions, right? Estimation of labels, of plus or minus, or of functions in general. But this already, what this implies too, is some kind of maximum principle, right? This already gives some kind of maximum principle, and minimum principle, which people also, which there is a lot of also in differential equations, right? There's a maximum principle. Right? In particular, it's not hard to see that the maximum and the minimum needs to be attained at labeled points, which makes a lot of sense, right? It would be very strange to have, you know, unlabeled points getting a label of 2 or 1.5, right? And so in particular, both the maximum and the minimum need to be attained at labeled points, right? I mean, because labeled points, of course, they don't have to satisfy this necessarily, right? And if you think about it, you know, if a point is the maximum, and it's the average of all of everything else, so it cannot possibly be the maximum unless everything is the same. So if a point has a non-zero connection to both a +1 label and a -1 label, for sure it cannot be, it needs to be less than 1 and bigger than -1, right? Because it's just an average of other things. And so for a point to be bigger than 1, it would mean that all its neighbors would have to be exactly the same value and also bigger than 1, and then all their neighbors and so on, and you would eventually see a label of 1 or -1, that would be a contradiction. So in particular, we see that fi is smaller or equal than 1 and -1 for all I. Right, so and the maximum and the minimum need to be attained at the labels. And so what we're going to do on part 2 is we're going to give a particular example motivated by Euclidean geometry and see sort of a strange behavior happening in some of the experiments. And Sobolev-Embedding theorem from differential equations is going to tell us about how to fix the issue and the sort of strange behavior that's going to show up and motivate some adaptations to the algorithm.